there. In this video, we are going to look at hypothesis tests that compare two population proportions. Now, we are assuming that these samples, the samples, are independent. So we have two independent populations from which we've selected two independent samples. Now, the samples need to be large enough so that the product of the sample size and the assumed value of the population proportion is at least 10. We also need to have the product of the sample size and 1 minus the assumed population proportion should be at least 10. We're going to have data then from two different samples, and so we are going to have two different sample proportions here. So we have two sets of successes, sample size, and then sample statistics. The test statistic we're going to use here is, or here I should say the sample statistic in this case, involves both of the sample proportions, and it's the difference between the p-hats. So when we conduct a hypothesis test comparing two proportions, we are actually talking about the difference between the two proportions. So the sampling distribution here is for the difference between P1 and P2. So we are doing a hypothesis test about a difference. So over here then, what we have is, well, I should say these would be hats. It's a distribution of differences between the sample proportions, and then in the middle will be the assumed difference between the population proportions. And what we are going to do is assume that this difference is 0. By assuming the difference is 0, notice that we're basically assuming that P1 and P2 equal each other since their difference would be 0. Let's look at the example and see what we can find out here. We are going to have two independent samples. So our first sample is a random sample of 150 runners who finished the New York City Marathon. And we are going to look at how many of those who finished were over 50 years old. Here we got a sample number of successes of 22 out of 150. So that's sample 1. Let's go ahead and summarize that data. Sample 1. We are going to identify our x1, our n1, and we will compute p1 hat. I like to do everything, write everything in its separate cell because we're going to have more computations than we had for the one proportion hypothesis tests. So it'll be easier to have these values available in their individual cells so we can just click on them when we are using them in formulas. So the number of successes, the number of runners who finished the marathon who were over 50 years old was 22, and our sample was 150 runners, the sample size. So p hat is going to be x1 divided by n1. Now, notice what happened here. It's just because I happen to have the size of my document such that when I clicked on a cell, the cell below it is unavailable for me to click on. However, I can see that that is cell B11, so I'll just type in B11, and you see that that's using the value in the cell even though you can't see it. So enter 0.147, almost 15%. Okay, sample 2. Oh, we've seen this one if you've watched my previous videos, we have here the sample of students who completed 4 years of college and how many of them smoked. So we have our 785 college graduates, of which 144 of them were smokers. So let's summarize sample 2. So sample 2, X2, N2, and P2 hat. So number of successes, that's the number who smoke. Remember, quote, success doesn't have to be a positive thing. In this case, it's how many smoke. So 144. The sample size, 785. So notice that our second sample has a much, much larger sample size than sample 1. We'll see how that affects things. Now we can compute P2 hat. So that's the 144 divided by the 785, which is contained in cell D11. And we get 18%, 0.183. So we can see that we're looking at about a 3% difference, right? It's just easier to work with these numbers to 2 decimal places, so we can just look at 15% and 18% and see that there's a 3% difference between these two sample proportions. So the question is that difference between them likely simply due to random sampling error, or is this difference large enough that it was unlikely to have occurred because of random sampling error, and therefore our assumption that P1 minus P2 is 0 is incorrect? So it says test the claim that a greater proportion of college students smoke, so that's 18%, than the proportion of runners over age 50 who finished the New York City Marathon. Now what's interesting about two-tailed tests is, depending on how you set up the claim and H1, you can make the test either a left-tailed test or a right-tailed test. So sample 2 is greater than sample 1. Equivalently, sample 1 is less than sample 2. I am going to write the claim as a less than, even though the problem was worded in terms of greater. I'm going to write the claim as the population proportion of P1 is less than the population proportion P2. This is saying that the proportion of runners over 50 who finished the New York City Marathon is significantly less than the percentage of college graduates who smoke. And if there is a significant difference, we say that the difference is statistically significant. Our claim then is a less than, so we will be doing a left-tailed test. So the null hypothesis is always equality, and here we are testing that P1 minus P2 equals 0. So we are testing the claim, or the assumption, we're testing the assumption that there is no difference between the population proportions from which the samples were drawn versus the population proportion from sample 1 is statistically significantly less, or I should say significantly less than the population proportion from which we gathered sample 2. This is a less than. Think of it as an arrow pointing to the left, reminding us that this is a left-tailed test. Let's write down our alpha, and that's 0.025. Okay, so our alpha is 0.025, And now we can do our computations. Notice we've already done some of them. We already computed P1 hat and P2 hat. So what we're going to do now is find the value of the sample statistic. And since we have two different sample proportions, we create a single sample statistic by taking the difference between the sample proportions. We want to make sure that we do this in the same order as we've written our alternative hypothesis. So it has to be that P1 minus P2 is, P1 hat minus P2 hat will be the sample statistic for the difference. So the difference will be in the same order as you have it written in your alternative hypothesis. So I'm going to take P1 hat and subtract P2 hat. We had already seen or noted that the difference between these was 3%, but since we have P1 hat less than P2 hat, we're going to have a sample statistic that is negative, right? Negative 0.04. So remember, and let me go ahead and draw it again. What we're working with here is a sampling distribution of differences between two proportions. Okay, so it's the sampling difference, the sampling distribution for the difference between proportions. We are assuming here, based on this null hypothesis, remember that is our assumption, we are going to assume that P1 minus P2 equals 0. So notice the assumption is that the middle here is equal to 0. Therefore, the values to the left of the mean are negative, and the values to the right of the mean are positive. Now, we had said the difference here was about 3%, but it looks like when you round it, it rounds up to 0.04 or 4%. So that's interesting. Just because I am curious, I am going to see the additional decimals. See, 3.7%. Okay, so we have a sample statistic that is to the left of the assumed mean of the sampling distribution. So I'm going to go ahead and draw it here so you can see what we have here. Whoops. Oh, I see what I'm doing. What we have here then is a sample statistic that is creating a left tail. So if the sample statistic is to the left of your assumed mean or assumed value, right, coming from the null hypothesis, then we will do a left-tailed test, and we're basically claiming that our sample statistic is less than the assumed value of 0 from the null hypothesis. So we have a left-tailed test, and so we need to find the p-value here. And since it's a left-tailed test, and this is a normal distribution, we will not have to worry about using complements and doing 1 minus. We will just be computing a straight norm dot dist. But before we get to the p-value, there's a couple of other computations we need to do. We have two samples, and we have a sample statistic that compares two samples, right? Sample statistic that compares two samples. Too much. Okay, so Let us then think about what we need to do for the standard error. Okay, for the standard error. If we have two separate samples and our sample statistic is the difference between these two different samples, we are going to need to have a standard error that contains the information x1, n1 and x2, n2. We need to contain the information from both samples. Let's go over to this tab and look at then what that standard error looks like. Before, we had a standard error that was computed by doing the square root of p times 1 minus p over n. I'm sorry, p times, the square root of p times 1 minus p over n. All right, that's what we were doing before. Well, how are we then going to work out with two of them? We basically just add those two things together under the square root. Well, I shouldn't say that. We're going to actually have to make a new computation that includes all the information from both samples to compute our new standard error. Now, what we are going to do, instead of using P1 and P2 right in, or X1 and N2 and P1 hat and P2 hat right in the standard error formula, we use something called the pooled proportion inside the formula. And the pooled proportion is what we get when we add the number of successes from the two samples together and divide that by the sum of the sample sizes. Why can we compute a pooled proportion? The reason we compute a pooled proportion is because by assuming that the difference between the population proportions is zero, we are assuming that the two population proportions are equal. So under this assumption of equality, we can pool our data and compute a pooled proportion that we then use for the standard error formula. All right, so the next question might be, well, if we're already pooling the data, why do we have to have a sum of two different pooled times 1 minus pooled over n? Why two terms if we're using the same pooled in both? Well, if you look, notice that the denominators are different. They correspond to the sample sizes. So the reason we have to use all this information is because the sample sizes will be weighted differently in the computation. For us, our second sample had a size of 785 relative to the first sample, which is 150. So it's much larger. Therefore, here we're going to have a much larger effect from the second sample in making this part of the equation smaller, right? Denominator bigger, numerator's the same, then this fraction will be smaller. So this is contributing less to the variation in the distribution than the smaller sample size, right? This has less variation than the data due to the smaller sample size. So even though we're pooling our data into one single proportion that we can use in the formula because we're assuming that the populations are equal, we have to take into account that their sizes were different. So this is our standard error formula, and it uses the pooled proportion. So we need to now compute the pooled proportion. So pooled, I'll just call it pooled. So this is going to be the sum of the successes, x1 plus x2, and remember to enclose that sum in parentheses so that the addition is performed before the division by the denominator, which itself must be enclosed in parentheses so that the addition is performed before this division. So parentheses n1 plus n2. And I forgot to put my plus. So n1 plus n2 close parenthesis. Notice how the color coding works in Excel. I think this is really cool. So the first thing I highlight is blue, the second is red, then it goes to purple and green. It's not going to work if you're colorblind, but otherwise it's great. So here's our pooled proportion. All right. Now, the difference between 15 and 18 is about 1.5%, and this looks almost the same. But remember, I told you that the sample sizes are weighted differently, as these are different sample sizes. If these sample sizes were exactly the same, then we would probably, well, we can find out later, but we would be able to, basically, it would have been like doing them, the two pieces here would have had exactly the same value, all right? But here, let's see, if we were just to take these pooled proportions and find their average, so add them up, divide by 2, 0.165, to one decimal place they'd be similar, but when we look at the additional decimal places, we should give these another additional decimal place each as well, since we did 2 their difference. All right, we can see that the average 0.165, all right, is not the same as the pooled of 0.177. Okay, so you cannot simply take the average of the two sample proportions to get your pooled proportion. Okay, all right. Now let's delete this. Okay. If however these were identical sample sizes, notice that when we compute the pooled proportion, all right, we'd essentially get the average of them. All right, now we are ready to compute the standard error. So this is going to take a little more typing, but it is not bad. So we want the square root of pooled. I want to be able to just click and not have to type that every time. So let me change the size and see. Ooh, that's way too big. Let's see if I can change this a little bit so that when I click on one cell, it doesn't hide the other one. Oh, it already is. Okay, this is what I'm going to do. Now I'm trying to just make it easier on myself so I can just click on that. Just going to put it in this cell that's not directly beneath the other one. So it doesn't have to be lined up. And that'll actually make it easier. So I can just click on the cells. So square root of pooled times grade 1 minus pooled. All right, I really don't want to have to type in the cell designation every time, although I probably would be done with the computation by now if I just had. But we want to compute the standard error as the square root of pooled times, open parenthesis, 1 minus pooled, close parenthesis, divided by the sample size of the first sample, plus, we do the whole thing again, but we divide with the second sample size. So this part will look the same because we're using pooled times parenthesis 1 minus pooled close parenthesis divided by the second sample size n2, and then don't forget to close your final parenthesis. Again, notice the color coding here. I didn't point this out before, but these inner parentheses are in red, so the red parentheses are a unit and they're complete. And then the square root was marked with a black parenthesis, so this black closed parenthesis is the one that corresponds to that black open parenthesis. Okay, so here is our standard error, 0.034. Okay, so we have a sample statistic of negative 0.037 and a standard error of 0.034. Let us now find the p-value. We already know we are doing a left-tailed test, so we do not have to use the rule of complements. We do not have to do a 1 minus. We are simply going to do a norm dist. So equals norm.dist of x is the, make sure that you don't keep that one lit. X is our sample statistic. So when you see this little x here, that always means your sample statistic. All right, comma, the standard error, which of course is hidden, and that is in cell B21, comma, oops, sorry, got ahead of myself. The mean, I jumped to the standard deviation. The mean is next. And remember, the mean is a value in the null hypothesis. It is the assumption we are making in order to describe that normal distribution. So the value from the null hypothesis always replaces the mean, just like the sample statistic is the sample statistic x here. So what I want then is the mean, which we are assuming to be 0. So whenever we are comparing two proportions, we're always assuming that their difference is 0, so we will always have the mean as 0 in the formula. Okay, now we're ready for our standard error, which is in B21, comma, always true, close parenthesis, 0.14. Okay. Again, this is a large p-value. It's a lot bigger than 0.025. So the decision is p-value is greater than alpha. So what we're going to do is do not reject the null hypothesis. So again, we are supporting it, but it's a weaker support than if we had rejected it and supported the alternative. That would be a stronger support. So we do not reject the null, okay? And therefore, the conclusion, if we didn't reject the null, we didn't support the alternative, and the alternative is the claim, so we didn't support the claim. So the sample data do not support the claim. All right? The sample data do not support the claim. Okay, that is a two-tailed test. If the sample data did not support the claim, I'm going to talk about this just slightly more. So remember, we were talking about that difference at 0.037. Was it a significant difference or just likely due to random sampling error? Well, if we did not reject the assumption of equality, then the difference, and by difference, I mean this sample statistic difference, is likely due to random sampling error. All right. If we had gotten a small p-value, which means smaller than alpha, and we rejected the null hypothesis and supported the alternative, then the difference would be statistically significant. But in this case, it's not statistically significant. it's likely due to random sampling error. Thanks for watching.